Good afternoon, everyone. Thank you for joining us on the webinar today. The NOAA Central Library is very excited to have Dr. Vladimir Krasnopolsky giving a presentation on machine learning for numerical weather prediction. Dr. Krasnopolsky received his master's in theoretical and computational physics and a PhD in theoretical nuclear physics from the Moscow State University. And since 1990, working in NOAA, he has developed multiple machine learning applications for numerical weather and climate prediction. We will be holding questions until the end of the presentations. Please put them into the question panel and I will be reading them out. If your question is not answered in our time frame, please put it in the question panel and we will send it on to Dr. Krasnopolsky at the end. So with that, I will turn it over and take it away, Vladimir.
Good afternoon. In my talk, I'll give an overview of machine learning applications for numerical weather predictions. Of course, so many applications has been developed that I cannot give you a detailed overview of all of them. So I will give an overview of major groups of these applications. I will talk briefly about each of these groups, and give you several references for original publications, and then at the second part of my presentation, I will show you several examples which will illustrate the first part of my presentation. This slide shows major points which I would like to make during the presentation. First of all, I would like to emphasize that machine learning is not something new and unknown for numerical weather prediction. People in numerical weather predictions and in related fields such as satellite remote sensing, satellite data processing, have been using machine learning for more than 25 years, and a lot of very interesting and successful machine learning applications has been developed. Why it's important? It's important because it shows that our current expectations and plans for using machine learning in numerical weather predictions and related fields are built on the solid basis of previous experience with machine learning in numerical weather prediction. I would like to show you also that machine learning is a toolbox of versatile nonlinear statistical tools. It's also important to understand that machine learning can solve and alleviate many problems which we face now, but it cannot solve all problems or any problem. It has very broad but limited domain of application. Now, because we are talking about machine learning, what is machine learning? Machine learning is a subset of artificial intelligence, and machine learning algorithms build nonlinear mathematical statistical models based on training data. This is why machine learning very often called learning from data approach or statistical learning. Machine learning has a rich toolbox of tools which includes there are several tools which are shown here, but there are many more. It's support vector machines, decision trees, artificial neural networks or simply neural networks, Bayesian neural networks, genetic algorithms. I put neural networks in the center of this figure because 95% or even more of applications developed, machine learning applications developed in our field have been developed using neural networks. And there are many different types of neural networks. Shallow neural networks, DNN, which is for deep neural networks, CNN, which is for convolutional neural networks, RNN, which is for recursive neural network, and so on and so on. Now, as I said, we use neural network for more than 25 years. Why we start talking so much about neural network now? Because now in numerical weather prediction, we are in the middle of the crisis. And this crisis is caused by several major simultaneous challenges which emerged recently, or not relatively recently, as I said. First big challenge is data change. Left picture shows integration weather satellites, meteorological satellites around the Earth, near the Earth's face. And this is old, relatively old picture. It's 3 or 4 years old. Now there are much more satellites. Sometimes like a month ago, SpaceX launched 60 satellites in one shot. So a number of satellites increases, and each of them generates tons of data. And the right picture shows that unfortunately it's also not very new. It's from 2016, and that time only 3% of available data were used in numerical weather prediction, were assimilated in numerical models. Current number is even less, it's less than 1%. So an avalanche or tsunami of data is moving toward us, and we need to do something with it. And we hope that machine learning response to this challenge helps us to deal with this data challenge, because machine learning showed that it can speed up data processing by orders of magnitude, improve extraction of information from the data, enhance assimilation of data in data assimilation systems. Next challenge is resolution challenge. We try to extend forecast horizon of our models. We try to improve forecast skills, and to do it, we increase resolution of models. And left figure shows horizontal axis shows resolution. Left vertical axis shows number of computer cores which are required to support this resolution. And right vertical axis shows power consumption of this number of computer cores. Red line shows affordable power limit. And you can see that ensemble systems, which are shown here, have already hit this power limit. And it means that we cannot increase the number of ensemble members, or to increase the number of ensemble members, we need to reduce the resolution of these members. So, and single member forecast systems will hit this limit very soon. In addition, processors are getting faster. This figure stops at 2006. It shows clock speed, dependence of clock speed of processors on time. But to the best of my knowledge, during the last decade, no major breakthrough was made in increasing processor powers, speed. We expect machine learning can respond to this challenge with speed up of model calculations. and I will show you how we can do it. A related challenge is model physics challenge. With increased resolution, scales of subgrid processes become smaller and smaller. And what does it mean? These subgrid processes still have to be parameterized, but physics of these processes is usually much more complex and not very often not very well known. So this parameterization become complex and slow, not very accurate. And machine learning can help us speed up calculations of these slow parameterizations. We're developing fast machine learning emulation of existing parameterization and fast new machine learning parameterizations. This next slide summarizes machine learning applications that has been already developed for numerical weather prediction and related fields. Each panel shows a group of applications. Upper left for data utilization, upper right for the enhancement of data and images, then initialization of models, data assimilation, fast emulations of model physics to speed up model calculations, new parameterizations of model physics, enhanced post-processing techniques. All these different applications has been already developed, and for all of them, machine learning can be used. But you can see that they are very different. Question arises why machine learning can be used for all these very different applications, for all these very different problems. What is common for them? And one thing is common for them. They all are mappings from a mathematical point of view. And what is mapping? Mapping is a relationship between two vectors from different vector space, vector x and vector y. Symbolically, it can be written as a function, but in this case, both y and x are vectors. And why it's important? Because machine learning tools are generic tools to approximate complex nonlinear mappings. Neural networks supported by machine decision trees are generic tools to approximate complex nonlinear multidimensional mappings. Now, as I told you, 95 or more percent of applications, machine learning applications developed in our field, have been developed using neural networks. Let me introduce the simplest neural net, which is a building block for more complex neural networks. And understanding of this simple neural net will help you to understand more complex machine learning tools. In general, neural net is a network of similar or identical units, which are called neurons. And this unit can be arranged in neural net in many different ways. And the simplest way to arrange these units if arrangement in layers and multi-layer perceptron. Each particular arrangement of neurons is called neural network architecture. And multi-layer perceptron is the simplest architecture. And it consists of one input layer which takes in components of vector x. It has always one output layer which generates components of output vector y. And it has always one or several hidden layers with hidden neurons. A neural net with one hidden layer is called shallow neural net. With many hidden layers, deep neural net. But this material spectrum, which I show you, is simplest material perceptron shallow neural net with one hidden layer. And let's see what happens inside these neurons. Each neuron has many inputs and one output. And generic neuron has two parts, linear part and nonlinear part. Linear part calculates linear combination of inputs. And then the result of this calculations go into nonlinear part as an argument for nonlinear activation function, high scope activation function, which produces neuron output. Now, generic neuron has two parts, as I said, linear and nonlinear, and neurons in hidden layer have generic neurons with two parts. But in output layer, we can simplify our architecture and take neurons which have only linear part. This neuron can be written symbolically in this way, and if we specify activation function, for example, hyperbolic tangent is one of the favorite activation function which people use, then this neuron can be written analytically as an analytical expression. Also, when we selected linear neurons in output layer, each output becomes a little linear combination of outputs from neurons in hidden layer. Okay? And if we substitute for TJ with this analytical expression, we can write the entire neural net as an analytical expression. And you can see that it's nonlinear too. Outputs depend non-linearly on inputs. And it's actually a nonlinear mapping. It maps components of input vector into components of output vector. And for particular mapping, we need to find coefficients A's and B's from data. And this process is called training. During neural training, we find coefficients A's and B for a particular data set which is given to neural net. Now, as I said, it's what is important that it's mathematically proven that the simplest neural net can approximate any, emphasize any, complex nonlinear multidimensional mapping. So it's so powerful that even this simple neural net can approximate any such mapping. And of course, more complex can do it even better. Now, let's talk about these big classes of big groups of ML applications which I was talking about. First group is ML applications for model initialization. All these applications, as I said, has been already developed, and I will give you at least one reference to original paper where this application has been published. There are many more references. I selected one for the subject here. In most of cases, it's first reference from this application developed the first time. For satellite retrievals, fast retrieval algorithms based on inversion of fast machine learning simulation of data transfer models have been developed. As you know, physically based retrieval algorithms are based on inversion of radiative transfer model. Radiative transfer model are complex and slow. So this physically based retrieval algorithm are slow. Neural network and the machine learning can provide fast emulations for alleviated models, which can be used in inversion and provide fast machine learning retrieval algorithms. A lot of algorithms are based on data when physics of the processes involved are not very well understood. And in this case, I will show you such an example. Neural network machine learning works much better than regular tools which we usually apply. For direct assimilation of satellite analysis, we need fast forward models because forward models are iterated many times in data assimilation systems, and machine learning can provide such fast forward models. Machine learning tools can enhance assimilation of surface observations. Machine learning empirical models and operators, observation operators, can provide through instantaneous propagation of surface signal vertically in atmospheric model or in ocean model. Also, machine learning provides very useful tools for filling gaps in satellite data, satellite retrievals. Next big group of application is machine learning for numerical model. A very important group of application is fast and accurate machine learning simulations for model physics. Model physics is computational bottleneck. I will talk about it in details a little bit later. And machine learning provides tool for accelerating calculation of model physics. In some of these cases, for example, in this case, when machine learning neural network was used to emulate nonlinear wave interaction in the wave glitch model, speed up is fivefolds of magnitude. In other cases, it's 1 or 2 order of magnitude, but still it's very significant. There are many other very interesting applications that have been developed or under development. New machine learning parameterizations can be developed when existing parameterizations are not satisfactory enough. For example, in this work and in several other works, a convection parameterization for general calculation model was developed by learning from CRM simulated data, from cloud resolving model simulated data. Machine learning emulation for simplified general circulation model has been developed in several works, and it allows to create statistical models for short-term forecast. Next very rich group of applications is applications for nonlinear ensembles. I will show you examples for all of these applications. That's why I don't talk about them now to save time. Machine learning can be used for nonlinear bias correction and even for improvement model forecast. For example, climate forecast for week 3 and 4 is the worst case for forecast, but application of neural net can improve this forecast in this very poor situation.
Hi,
Now,
Vladimir. This is Katie. I'm just going to interrupt you for 1 second. We've got some comments that your audio is a little low. Could you either speak up or speak a little slower, more clearly? Maybe that's the issue.
Okay.
Thank you.
Okay, let me show you now several examples which I promised. First example is for satellite data, for working with satellite data. when we are talking about using satellite data for assimilation in numerical model, it's used in two different ways. Physical parameters can get assimilated, or radiances measured by satellite can be assimilated directly. To create geophysical parameters from satellite data, we need retrieval algorithms or transfer functions, which are mappings between satellite measurements and geophysical parameters. For direct assimilation, we need forward models, which are also mapping between geophysical parameters and satellite measurements. And because both of them are mappings, machine learning tools like neural network can provide fast and accurate retrieval algorithms and fast forward model for direct assimilation. Here is an example of SSMI wind speed retrievals. In this case, physics of processes involved is not completely understood, and retrieval algorithm is based on data, and standard tool for developing such empirical retrieval algorithms is regression technique. And these two figures show tropical storm, not tropical, I'm sorry, mid-latitude storm in Indian Ocean. And left panel shows regression, retrieval obtained with regression. Right panel shows retrieval obtained with neural network algorithm. What happens with regression algorithm? Situation in the center of the storm is very nonlinear, so algorithm transfer function becomes very strongly nonlinear, and a regression algorithm cannot handle such kind of nonlinearity, and it confuses high level of moisture which exists in the center of the storm with high wind speed, which also exists in the center of the storm. So it produces here funny retrievals which are flagged by quality control system. So in this case, we miss mostly energetic, mostly interesting for data assimilation in terms of impact, part of data. Neural network algorithm can handle this high level of nonlinearity and correctly retrieves, easily resolves difference between high moisture and high wind speed, and produce correct retrievals practically everywhere except very small areas. You can see these white areas where cloudiness is so heavy that macro radiation from the surface simply doesn't penetrate clouds. It's physical image for retrievals in this case. Second example is fast model physics. So symbolically, atmospheric model can be described by this equation. And atmospheric model actually is deterministic first principle model based on 3D partial differential equations on the sphere plus set of conservation laws, mass, energy, momentum, weather work, and so on. And model contains two major parts, model dynamics, which is actually resolved physics, and model physics, which is effective description of subgrid processes, which a model cannot resolve directly because the scales of these processes are smaller than the grid size, the resolution of the model. And this part of the model is computational bottleneck. Even in modest resolution, models takes more than 50% of total computation time. and with increased resolution, it takes more and more time, and people who work with models are forced to do different tricks to bypass this problem of increasing computation time for model physics. They calculate physics not at each time step or not at each grid point and then interpolate. So, but all these tricks reduce forecast skills of the model. So, and solution which machine learning can provide is fast machine learning simulation for model physics parameterizations. How this simulation can be developed? This figure shows a model with original physically based parameterization. And we want to develop fast neural network emulation of this parameterization. What do? We run model with original parameterization long enough to simulate representative training set. We write down inputs and outputs and save inputs and outputs for original parameterization when it runs in the model. And then we take this training set offline and train neural network emulation and validate it on an independent part of this training set. And then final test will be running parallel runs. We substitute original parameterization with neural network emulation and run in parallel this model and model with original parameterization and evaluate the difference. In perfect case, difference should be zero, but it always not zero, of course, but it should be small enough. And these neural network emulations perform, I told you, several orders of magnitude faster. What is the secret? What is the magic of this fast performance? As an example here, I show long wave radiation parameterization. And this is original parameterization. And each time step in each grid point, all this number crunching should be performed. This number crunching includes calculation of integral equations, radiative transfer equations, calculation of radiative fluxes. And to calculate radiative fluxes, you need to know the properties of the atmosphere, and they are calculated solving integral differential equations. And I repeat, all this number crunching should be performed at each grid point, at each time step. And it's not surprising that this parameterization becomes computational bottleneck in model calculations. When we substitute this parameterization with neural network emulation of this parameterization, again, at each time step, at each grid point, we need to calculate the simple sum of hyperbolic magnitude. Of course, it's orders of magnitude faster. But of course, we still need original parameterizations. We need them to generate training set or training of the simulation to find A's and B's coefficients of this neural net. But after we find this coefficients, we can run model with neural network emulation, and that will be significantly faster. It will be faster, but what kind of accuracy can you expect? Will it be sufficiently accurate? This slide shows output of long wave radiation. Output of long wave radiation is profile of heating rates. And this slide shows three such profiles. and complexity of profiles increased from the right to the left. It shows each picture, each panel shows three curves. Black curve is a profile generated by original related transfer parameterization. A red curve is profile generated by neural network with one hidden layer with 100 neurons. Sorry. And blue is profile generated by neural network with 150 neurons. The more neurons we have in hidden layer, the better is accuracy of approximation. So, and you can see that both neural networks perform very well. But for these very complex profiles, in some cases, red neural net is not completely good. But blue neural net improves results and is almost perfect. So next slide shows approximation statistics and speed up for long wave radiation and for short wave radiation for our Ensemble, CFS, and JFS models. It shows systematic error, systematic difference between neural network and radiated transfer parameterization, which is almost zero. It's very important because systematic error is what mainly accumulates in when you put these neural nets in the model and run the model. And next row shows RMS difference, which in this case, because systematic error is zero, it's purely random error. And last row shows speed up factor. On average, long wave radiation neural network is 16 times faster than original parameterization, and short wave radiation and then is 60 times faster. But for cloudy condition, they are even faster. Why? Because original parameterization becomes slower under cloudy condition, but neural networks performs takes the same time for any cloudy condition. So random error, RMS error, are small, but model is nonlinear. Even small random error may accumulate in the model. And to test it, to check it, we need the final test, parallel run. And this slide shows you parallel run, which was performed with Ensemble climate forecast system, 17-year run. It was run for 17 years. One number of parallel run, one model with original parameterization of parallel run, with original RR10 related transfer shortwave and long wave parameterizations, and another run with our neural network emulations. And lower left panel shows the difference. And the difference is small, but the question arises if it's small enough to show that it's can be considered as negligible, this difference. We ran another parallel run with two runs. Both of them have no neural network in them, both with original and late transfer parameterizations. But one run was run before change of version of our compiler. It's a routine change in any forecast system. And the second run was run after change of version of our compiler. And lower right will show the difference between these two runs. Again, I emphasize there is no neural network there. It's own original organizations related to shared organizations. So nobody can argue that this difference should be considered as negligible because changes of versions of Fortran compilers and libraries are routine changes in the models. So you can see the difference are comparable. So we can say that neural network introduces a negligible difference in forecast when you substitute original parameterization with neural network emulation. Another very, I think, promising application is calculating ensemble mean. There are many ensemble systems in modern numerical weather prediction systems, and usually the final step after calculating ensemble members is conservative ensemble or simple arithmetic mean of ensemble members. This arithmetic mean cannot extract completely all information which is in ensemble members. There are a lot of nonlinear relations and relationships with ensemble members which this arithmetic mean simply missed. And if we have past data and archive for ensemble members and past data for observations corresponding to these ensemble members, we can use neural network. We can train neural network to produce nonlinear ensemble averaging. To do it, you give ensemble members its inputs to neural net and train output on observation data. In this case, you force neural network to produce optimal ensemble average, to produce result closest to observation. And very interesting detail here is that in this setup, you can use additional data, which for example, from physical consideration, we know that these data are important, give important information for your output. In conservative ensemble, you simply don't have any place to introduce this additional data. Let me show you several examples. Here is example of multimodal nonlinear ensemble for 24-hour precipitation forecast over continental US. We have 8 models, international models, which produce forecasts for precipitations over continental US. Also, we have ground truth uses. This data is ground truth. It's Climate Prediction Center analysis for precipitation. And it's shown here at left, upper left, right. And upper right shows conservative ensemble, simple arithmetic mean. And you immediately can see problems with this ensemble. It diffuses features, reduces maximums, diffuses fronts, and produces a lot of false alarms, false low-level precipitation fields. Lower left shows neural network ensemble, nonlinear neural network ensemble, which is, as you can see, much better. It doesn't reduce maximums if you compare. It produces sharp fronts and reduces significantly false alarms. And what is interesting, in this case, we can compare this 24-hour forecast, nonlinear forecast produced by neural net with human-produced forecast produced by human analysts who uses much more information. In addition to model fields, analyst uses satellite images, radar images, and a lot of observations. But you can see that a human being and neural network produce very similar forecasts. And in some cases, like here, for example, I think neural network forecast is better than human forecast. Next example is a sub-global wave in Ensemble global wave ensemble system, we have 21 ensemble members. And this system produces forecast for 3 variables: wind speed, 10 meters, significant wave height, and peak wave period. And upper row shows RMS error as a function of forecast time in days, and lower row shows correlation coefficient as a function of forecast time. Black curves are ensemble members, and red curve is conservative ensemble arithmetic mean, and green dashed curve is neural network forecast. And you can see that neural network improves all forecasts for all 3 variables. And if you look at, for example, the relation coefficient for accuracy at day 10 for neural net and compare with the red curve, you can see that at day 10 accuracy of neural network forecast is the same as for day 5 or 6 for regular ensemble, standard ensemble. It means that neural network gains 4 days in forecast accuracy. Next example shows machine learning corrections for hurricane threatened intensity. I don't have time now to talk about this example. It's a pilot project. Neural network was trained on 16 storms and applied to independent storm. And as you can see, red is conservative ensemble, blue is neural network ensemble, and neural network improves or reduces errors in track forecast and reduces errors in intensity forecast. Intensity characteristics are maximum wind speed and minimum sea level pressure. And here this is 0 here, and this is 0 here. So neural network significantly reduces errors as compared with conservative ensemble. Now, in conclusion, as I tried to show you, machine learning is a generic and versatile artificial intelligence technique. A lot of machine learning successful applications have been developed in numerical weather prediction and related fields for model initialization, data assimilation, model improvements, for postprocessing of model outputs. So, and these applications allow to improve utilization of data and data assimilation, improve post-processing, speed up model calculations, which is what is important that this speed up can be used for many good purposes. You can improve parameterizations of physics. You can take slower parameterization, which cannot be applied now, and after emulation with neural network or other machine learning technique, they become affordable. Develop fast interactive chemistry and biology, increase number of ensemble members in ensemble, and increase model resolution. Also develop better parameterization. However, there is no free lunch. You need to understand well understand what is the domain of machine learning applications, and don't go beyond it. Don't try to apply machine learning to some problems which are not for machine learning to solve. And as any statistical models, machine learning require data, and they require more data than linear statistical models because they need additional data for validation. As any statistical model, machine learning models should be periodically updated to changes in the environment. So interpretation of coefficients of machine learning models is not obvious in the same way as interpretation of nonlinear statistical parameters is not obvious. So, and machine learning may not work in many cases. For example, if you don't have sufficient suitable data, if you don't have access to the data, if you have data bias, what does it mean that your data is not representative? They don't represent all set of possible situations which may have. We have also, in many cases, privacy limitations. If task is badly chosen, so it's beyond this domain of machine learning application. If machine learning algorithms are not properly used, if you have lack of resources, if you don't have sufficient memory, sufficiently fast computers, etc. So this is what you need to understand when you try to apply machine learning to your problems. So thank you, and if you have any questions.
Thank you so much, Dr. Krasnopolsky. If anyone does have questions, please put them in the question panel, but we do have one already. So I will try to do this question justice. So Dr. Krasnopolsky, how many A/B parameters have been actually used in the examples shown?
Oh, number of parameters depends on the architecture neural net. For example, for retrieval algorithm, we had only 5 inputs and 4 outputs and 12 neurons in one hidden layer. So the number of parameters was several hundreds. For long wave radiation or short wave radiation, we had several hundreds of inputs and about 150 of outputs. And as I showed you, about 100, 150 neurons in hidden layers. So the number of parameters was about several hundred thousand. And what it means, the number of parameters is dimensionality of space for neural network training. Neural network training is nonlinear optimization of error function. And in this case, when you have, for example, 100,000 of neural network parameters, you perform optimization in the space with dimensionality of 200,000. So it's very challenging problem, even for modern computers. But for smaller neural network, it's much faster and much simpler.
Okay, so there isn't like a typical value of the number of matching coefficients.
Yes, it
Okay.
depends on the task, on the problem.
Okay, thank you.
Actually, general answer would be that complexity of your neural net should respond complexity of the mapping you are approximate. But it's easy to estimate complexity of that, but it's very difficult to estimate complexity of the mapping, and it's usually a matter of trial and error, or how you choose the number of parameters.
Okay, thank you. I am not seeing any other questions on the line right now. Oh, no, we do have a few coming in, sorry. How do you detect and handle points at which the inputs to the trained neural network are outside the valid domain for the neural network, or how far is too far?
Okay, it's in general, it's very difficult to detect, but usually for training, you use or observe parameters, which are by nature put in physical domain, proper domain, or you use parameters simulated by the model, and model because it contains physical equations and physical parameterizations also automatically puts your inputs in a physical domain. So in this case, you don't care about uh, checking if your parameters are inside or outside. Of course, if your training set is not representative, so it means that neural network was trained only in the part of possible domain. And then the replication process, you meet a situation which wasn't represented in the training set. Then problem arises.
Okay, thank you. We have a few more questions. Could you give a few examples about the case or the domain where machine learning is not good for, where a user needs to be careful?
Actually, even if you use observation data or simulated data, the simulated data is a little bit easier, but with observation data, this problem always exists. Extreme values are underrepresented, and you need to take care about these cases and how you care about these cases. Again, it's problem dependent, which problem you solve. With when you use simulated data, you can force model to run longer and with initial conditions. Playing with initial conditions, you can force it to simulate extreme data. With observations, you cannot do it. So you need to perform some kind of quality control whenever you come out with.
Okay, thank you. Could you go into detail about the reasons or advantages of neural networks versus support vector machines or Bayesian networks?
Okay. With support vector machines, the advantage of neural network shows up immediately. With support vector machines, to calculate after you train support vector machines to calculate new output or new input or make prediction. You need to use entire training set. It means that you need to keep always entire data set, training set with you when you apply support vector machine. It puts very heavy requirements on memory and slows down application of support vector machine. With neural network, as you can see, after you train neural network, you forget about training set. You have neural network with fixed parameters, and that's it. It's fast and takes not so much memory. With Bayesian neural network, actually, I cannot give you a simple answer. I didn't have a lot of experience with Bayesian neural nets, and I think there are problems, specific problems for which Bayesian neural nets are better than regular neural nets, but I cannot say it. Thank you.
Okay, thank you so much, Dr. Krasnopolsky. We are running right up to time, and we do have two more questions. I am not going to ask those, but I will send them on to you, and you can respond to those people separately offline.
Okay.
I would like to thank everyone for joining us. Thank you, Dr. Krasnopolsky, and if
Thank you,
you
everybody.
yes, thank you. And if anyone wants to rewatch this, we will be posting it on the library's YouTube channel. Thank you and have a good day.